Notice how it neatly divides warm and cold sections of the CMB map. Now we transform our Molveda projection into a sphere and rotate our universe so that the S-shaped line of the ecliptic becomes the dark line across the center of the sphere. This plane, lying between the warm and cold areas of the CMB, will become the grid along which we fly through the entire visible universe. Over the past decade or so, we have seen out to the very limits of the observable cosmos. We've mapped its largest structure, the cosmic microwave background, the oldest light in the universe according to the standard Big Bang model of cosmology.
The colors we see here in the cosmic microwave background map are kind of like a weather map, showing hotter and colder, showing how hot the radiation is that's coming from different places. This is just radio noise from our own Milky Way galaxy. We're supposed to see the same number and types of hot and cold spots in all directions, because there is no up in the universe that's special. And that is sort of what we see, except not quite. This map here can be decomposed into what we call multipoles. You blur out all the little spots, and you still have the bigger ones remain. Like here is an area with a lot of blue. So when you smudge it, this will be one single big blue spot. Whereas when I smudge this, where there's a lot of red and yellow, it'll be one big blurry hot spot. On the very largest scales, we see a pattern of really big hot and cold spots which line up around a special axis.
Now we're in a position to look at the entire microwave sky. First, we introduce the multipoles. The dipole, usually attributed to a relative motion between our local system and the CMB itself. The quadrupole, the north and south ecliptic poles, and the spring and fall equinoxes. The S-shaped line represents the plane of the ecliptic, the plane of the orbit of the planets around the sun. Notice how it neatly divides warm and cold sections of the CMB map.